All right, let's dive right in. We're going to unpack a wild new theory today, one that looks at the vacuum of space, empty space, and says, what if it's not empty at all? What if it's a physical thing? It's a huge shift in thinking, but it might just solve one of the most stubborn mysteries in all of physics.
And that big mystery is this: why stop at 3? See, fundamental particles like the electron we all know and love aren't solo acts. They have two heavier, much more unstable cousins, the muon and the tau. We call them 3 generations of matter. And for decades, the standard model of physics has just sort of shrugged and said, yep, there are 3. It never tells us why 3. Why not 2? Why not 20? It's a massive loose end.
So to finally get an answer, this new idea tells us to stop staring so hard at the particles themselves and instead look at the stage they're dancing on. We have to rethink our most basic idea of what a vacuum even is.
Okay, so here's the core idea, and it's a big one. The vacuum isn't nothing. It's something. It has a real physical structure, a kind of hidden architecture woven into the deepest level of reality.
The theory is called vacuum elastodynamics, and what it's saying is that way down at the tiniest possible scale, we're talking the Planck scale, the universe basically acts like an elastic solid. Imagine all of space is filled with a huge, invisible crystal lattice. You can stretch it, you can squeeze it, you can bend it, kind of like a giant block of gelatin. And the crazy part is this isn't supposed to be an analogy. The theory says this is literally what reality is.
Right. So if the vacuum is this tangible fabric, then what does that mean for the particles living in it? Well, it means they're not what we've been picturing at all. Forget those little billiard balls or abstract points of energy. In this model, particles are basically imperfections. They're what we call topological defects in the crystal of space. The best way to think of it is like a tiny stable knot or a twist that's been tangled into the fabric of the vacuum itself. So an electron isn't just a thing in space. An electron is a localized, twisted piece of space. And this is where it all starts to click together so beautifully. What about mass? That quote sounds super complicated, but the idea behind it is incredibly simple. Mass isn't some mysterious property a particle just has. No, it's just the amount of energy it takes to twist the vacuum into that particle knot and keep it twisted. That's it. A bigger, more complicated knot takes more energy to hold its shape, and so it has more mass.
And that brings us to the most critical piece of this whole puzzle. Because if the vacuum is a real physical material, then just like any other material, it has to have a limit. You can only bend or twist something so far before it snaps.
I mean, think about it. A steel beam, a rubber band, literally anything you can touch. If you put enough stress on it, it will eventually yield, warp, and break. The theory of vacuum elastodynamics says the universe itself plays by the exact same rules.
And it even gives us the number. This number right here. This could be one of the most important constants in the cosmos. It's the universe's ultimate safety limit. It represents the absolute maximum amount of strain the fabric of space can take before it just fails.
Officially, it's called the Frankel yield strength. It's a term borrowed straight from materials science, which is pretty cool. Think of it as the ultimate red line for reality. If you try to twist a piece of the vacuum harder than this critical value, the whole structure just gives way. This number right here is what decides whether matter can even exist or not. Okay, so let's put all the pieces together. We've got a physical vacuum. We've got particles that are just knots in that vacuum. And we've got a hard and fast limit on how much you can strain that vacuum. Now it's time to solve our original mystery. So check out this table from the paper. It shows just how much strain each of those lepton generations puts on the vacuum. The first-gen electron, look at that. It barely makes a dent, a strain of just 0.0021. But then you get to the muon, and whoa, it's a much bigger strain. And then the third-gen tau particle, it's causing a massive strain of 0.1245. You can already see where this is headed, right? Each generation is cranking up the tension. And this graph just visualizes it perfectly. That blue curve is the vacuum stress level. Way down at the bottom, that first little dot, that's our electron, barely causing a ripple. The next dot up, the muon, is already putting some serious stress on the system. But look at that third dot, the tau. It's pushing the vacuum right up to the absolute peak of its strength, getting terrifyingly close to that red dashed line. That's our Frankel limit, the universe's breaking point. How close? Well, with the tau particle in the mix,
The vacuum lattice is stressed out to 98.6% of its maximum possible strength. Think about that. The three families of matter that make up everything, they use up almost all of the structural integrity the universe has to give. We are living right on the knife's edge.
Which brings us, of course, to the million-dollar question. What would happen if nature tried to make a fourth, even heavier, even more complex particle knot?
Well, the math doesn't lie. A hypothetical fourth-generation particle would try to induce a strain of almost 0.3. And now you can see the verdict in black and white. That number doesn't just creep over the limit of 0.159. It completely blows past it. It's not even close.
And the conclusion is just inescapable. The reason there's no fourth generation isn't because it's unstable or rare. It's because it's physically impossible. Trying to form that knot would twist the fabric of space so violently that it would literally break. You wouldn't get a new particle. You'd get a hole punched in the structure of reality. The vacuum itself would shatter.
So just like the paper says, that famous three-generation rule isn't some weird abstract law of quantum physics. It's a mechanical yield limit. It's the same reason a bridge has a weight capacity or an elevator cable is rated to hold a certain number of people. The universe has engineering specs, and 3 generations is all the system can safely handle.
This just completely reframes how you think about physics, doesn't it? It suggests the laws we observe might not be pure mathematics, but the actual engineering specifications for the material of our cosmos. And that leaves you with one hell of a thought to chew on. What other cosmic speed limits and structural load capacities are hiding out there, disguised as the fundamental laws of nature?